WAL, the unsung hero, how write-ahead logs power modern databases. Chapter 1, Introduction to Data Persistence and Reliability. Imagine a world where your bank balance could spontaneously disappear, or where your doctor's critical notes about your allergies vanished into thin air. Picture trying to board a flight, only to find your reservation gone from the airline system. While these scenarios might sound like the plot of a dystopian novel, they highlight a fundamental concern that underpins nearly every aspect of our modern, digital lives: the absolute necessity of reliable data. From the moment we wake up and check our phones, our day is orchestrated by vast networks of interconnected information. Our money, our health records, our communications, our social connections, our creative work, all of it exists as data. We perform countless transactions, both financial and informational, often without giving a second thought to how these digital interactions are meticulously recorded and safeguarded. This unquestioning trust is a testament to the quiet heroes working behind the scenes: databases. In the realm of digital information, two concepts are paramount: data persistence and data reliability. Think of them as the bedrock upon which our digital world is built. Data persistence simply means that data, once created or modified, will endure. It won't vanish when the power flickers off, or when a computer program crashes, or even when an entire server is shut down and restarted. When you save a document to your computer's hard drive, you expect it to be there the next time you open the document. When you post a photo online, you expect it to remain accessible for years to come. This enduring quality is what persistence is all about. It's the difference between information existing temporarily in the computer's volatile, fickle memory, RAM, and being firmly etched onto non-volatile storage, like a solid-state drive or a traditional spinning hard disk. Data reliability is a broader, more encompassing concept. It's not just about data being there, but also about it being correct, consistent, and accessible when you need it. A reliable database doesn't just store information. It ensures that your bank balance always sums up correctly, that your medical history remains accurate even after multiple updates, and that your flight booking is available to everyone who needs to see it at the same time. Reliability is about trust that your data is safe from corruption, distortion, and loss, even in the chaotic wake of unexpected system failures. We've all had that heart-sinking moment. You've spent hours crafting an important email, typing away furiously, perhaps lost in your thoughts, only for your computer to suddenly freeze or lose power. You restart it, hoping against hope, but the unsaved work is simply gone. Or perhaps you've seen a personal photo collection vanish due to an unforeseen hard drive failure. These personal anecdotes, small in the grand scheme of things, illustrate the very real and visceral fear of losing valuable information. Now, magnify that fear to the scale of vast organizations, financial institutions, or critical infrastructure, and you begin to grasp the monumental challenge that databases face every second of every day. Databases are the digital guardians of our critical data. They are complex software systems specifically designed to manage, store, retrieve, and update information in a way that respects the principles of persistence and reliability, even under immense stress. But how do they achieve this seemingly magical feat? How do they ensure that a vital update isn't lost if the power cord is suddenly yanked from the server? How do they guarantee that your money transfer either fully completes or is completely undone, leaving no partial, inconsistent state? The answers to these questions lie deep within the inner workings of databases, rooted in a fundamental technique that most users, and even many developers, know little about. It's a mechanism that acts as a silent, unwavering ledger, meticulously recording every intention, every change, every critical decision a database makes regarding your data. This technique is called the write-ahead log, or WAL for short. In the coming chapters, we will embark on a journey behind the digital curtain. We will explore the problems that WAL was specifically designed to solve, delve into its ingenious mechanics, and understand its pivotal role in guaranteeing the integrity, availability, and durability of the data that fuels our modern world. From ensuring your next online purchase is safely registered to powering the massive scale of global banking, the write-ahead log is the unsung hero. silently underpinning the reliability of nearly every digital interaction you have. Let's begin by understanding the foundational unit of work that the WAL so diligently protects, the database transaction. Chapter 2. What is a database transaction? Before we dive deeper into the mechanics of the write-ahead log, it's essential to understand the fundamental concept that WAL exists to protect: the database transaction. If you've ever interacted with a database, even if unwittingly, you've engaged in transactions. This seemingly simple term encapsulates a powerful guarantee that is central to data integrity. In the world of databases, a transaction is defined as a single, logical unit of work. It's a group of one or more operations, like inserting new data, updating existing records, or deleting information, that are treated as a unified whole. Think of it as a tightly bundled package of actions. The crucial principle here is the all or nothing rule. Either all the operations within that package are completed successfully, or none of them are. There is no in-between state. No partial results are allowed. To truly grasp this concept, let's use a classic example: transferring money from one bank account to another. Imagine you want to move $100 from your checking account to your savings account. This seemingly straightforward act involves at least two distinct steps in the bank's database: debit your checking account, subtract $100 from its balance; credit your savings account, add $100 to its balance. Now, consider what would happen if these two operations were treated as separate, independent actions by the database. Suppose the system successfully debits your checking account, but then, before it can credit your savings account, the power goes out, the network connection drops, or a software bug causes the database program to crash. In this disastrous scenario, your checking account would be $100 lighter, but your savings account wouldn't be $100 heavier. Your money would have simply vanished into thin air, and the bank's books would be inconsistent, no longer reflecting reality. This is precisely the type of nightmare scenario that database transactions prevent. When these two operations, the debit and the credit, are grouped together within a single transaction, the database makes a rock-solid guarantee: atomicity. This is the A in the widely recognized ACID properties of database transactions: atomicity, consistency, isolation, durability, which we'll explore in more detail in a later chapter. With atomicity enforced, the bank transfer example plays out very differently. Start transaction. The database acknowledges a new logical unit of work is beginning. Debit account A by $100. This change is typically held in memory or as a pending modification, not yet finalized on disk. Credit account B by $100. Again, a pending modification. Commit transaction. If both steps 2 and 3 have successfully been prepared, the transaction is committed. This signals to the database that all operations within this unit of work are complete and ready to be made permanent. Alternatively, rollback transaction. If at any point during steps 2 or 3 an error occurs, e.g., insufficient funds in account A or a system crash, the entire transaction is rolled back. This means any partial changes made during steps 2 and 3 are completely undone. It's as if the transaction never happened, and the database returns to the exact state it was in before the transaction began. The beauty of the transaction is that it simplifies complex operations. As an application developer, you don't have to write intricate code to handle every possible failure point in the middle of a multi-step process. You simply define the boundaries of your transaction, and the database takes on the responsibility of guaranteeing its atomic execution. This all-or-nothing principle is critical for maintaining data consistency. If a database allows partial updates, it can quickly fall into an inconsistent state where the relationships or rules between pieces of data are violated. For instance, in an inventory system, if an order decreases stock but fails to record the sale, the inventory count becomes inconsistent with the actual transactions. This can lead to incorrect business decisions, financial losses, and a complete breakdown of trust in the data. While many transactions happen behind the scenes, you implicitly interact with them constantly. When you book a flight, a transaction ensures that your seat is reserved and your payment is processed. If either fails, neither happens. When you check out your online shopping cart, a transaction handles the reduction of inventory, the charging of your credit card, and the creation of your order. All these actions must succeed simultaneously or be completely undone to maintain the integrity of the system. The database transaction, with its guarantee of atomicity, is the cornerstone of reliable data management. Yet, simply defining a transaction isn't enough. As we discussed in Chapter 1, physical failures like power outages can still disrupt these delicate sequences of operations. The next chapter will delve into these very problems, the challenges of data loss and inconsistency in the face of inevitable crashes, setting the stage for how the write-ahead log emerged as the elegant and essential solution. Chapter 3. The problem we're solving: data loss and inconsistency. In the previous chapter, we established the critical importance of a database transaction as an all-or-nothing unit of work. The concept of atomicity ensures that our bank transfer either fully completes or is entirely undone, never leaving an undesirable partial state. But understanding the concept of a transaction is one thing. Guaranteeing its safe execution in the real world, amidst the unpredictable chaos of hardware and software failures, is another challenge entirely. This is where the write-ahead log truly earns its stripes, as it addresses the fundamental problems of data loss and inconsistency that arise when systems crash. To grasp these challenges, we need to understand how databases typically handle data in terms of speed and permanence. Imagine data existing on a spectrum. On one end, we have RAM, random access memory. This is the computer's superfast working memory. Databases use RAM extensively, often in large sections called buffer pools or caches. When you request data from a database, it's often loaded from its permanent storage, like an SSD, into this buffer pool for quick access and modification. This is incredibly fast, measuring access in nanoseconds. However, RAM is volatile. If the power goes out or the system crashes unexpectedly, everything in RAM instantly vanishes. It's like a whiteboard where all your scribbles are erased in a flash. On the other end, we have SSD, HDD, solid-state drives, and hard disk drives. This is where the database's actual data files reside permanently. Data written here will survive power outages and system reboots. This storage is non-volatile. However, accessing and writing to disk is significantly slower than RAM, measuring access in microseconds or even milliseconds, potentially 1,000,000 times slower than RAM. It's like engraving on stone permanent, but takes time and effort. Databases are constantly balancing the need for speed, working in RAM, with the need for permanence, writing to disk. To maximize performance, databases employ a strategy of deferred writing. When you make a change in the database, e.g., update a customer's address, the database typically doesn't immediately write that change to the customer's record on the physical disk. Instead, it modifies the data page in its in-memory buffer pool. This page is now considered dirty because its contents in memory are different from the older, still clean version on disk. This deferred writing strategy is hugely efficient. Database operations often involve many small changes to different parts of data, and bundling these up before writing them to disk as a larger chunk reduces the number of slow disk input-output (I/O) operations. It's like collecting all your trash for the week and taking out one big garbage bag, rather than running to the dumpster every time you throw away a single item. However, this efficiency comes with a significant peril. What happens during a crash? Imagine our bank transfer example from Chapter 2. You've successfully committed the transaction. The $100 has been debited from account A and credited to account B. The database has even returned an OK, transaction committed message to your banking app. But internally, those changes only exist in the database's RAM buffer pool. The dirty pages, containing the updated account balances, haven't yet been flushed to the permanent data files on disk. Scenario 1, power failure/system crash. The server hosting the database loses power. Because the changes were only in volatile RAM, they instantly disappear. When the database server restarts, the data files on disk reflect the state before your transaction, effectively losing the committed change. You've lost $100, and the database is in an inconsistent state. This is a direct data loss scenario. Scenario 2, Database software crash. The database program itself encounters a bug or error and terminates unexpectedly. Again, all in-memory dirty pages are lost. The same data loss and inconsistency problem arises. Beyond simple data loss, there's an even more insidious problem, the torn page scenario. Database files on disk are organized into pages, e.g., 8 kilobytes, 16 kilobytes. When the database writes a dirty page from RAM to disk, it often involves a single, large write operation at the database level. However, the operating system and the storage hardware might break this down further into smaller physical blocks, e.g., 4 KB blocks. If a crash occurs during this write operation, meaning only part of the page has been physically written to disk, the page on disk can become a garbled mess containing half-updated information. This is a torn page. If the database tries to read this torn page on recovery, it might encounter corrupt data, leading to severe and difficult-to-repair data inconsistency. The challenge for a database system is monumental. After a crash, how can it reliably determine which transactions were fully committed and should be reflected in the data, and which were incomplete and should be completely undone? How can it rebuild the database into a consistent, trustworthy state, especially when some in-memory changes are gone and some on-disk pages might be corrupted? This is the abyss of uncertainty and inconsistency that database administrators dread. It's akin to trying to piece together a complex puzzle after someone has kicked the table, sending pieces flying, and even tearing some of them in half. Without a robust mechanism to bridge the gap between volatile memory and persistent disk, and to guarantee atomic, durable transactions, our digital world would be a house of cards. This is precisely the fundamental problem that the write-ahead log was engineered to solve. In the next chapter, we will finally introduce this elegant and powerful concept, revealing how it provides the crucial safety net for our valuable data. Chapter 4, Introducing the write-ahead log, the core concept. We've explored the critical importance of atomic transactions and the frightening vulnerabilities databases face when confronted with crashes and the volatile nature of memory. The problem is clear. How do we ensure that a committed transaction survives, even if its changes haven't yet made it to the permanent data files on disk? The answer is the ingenious mechanism known as the write-ahead log, WAL. At its heart, the write-ahead log is a deceptively simple, yet profoundly powerful concept. Every change to the database must first be recorded in a special, persistent log before that change is permitted to modify the actual data files on disk. This is where the name write-ahead log comes from. You write to the log ahead of writing to the data. Think of the WAL as the ultimate, unalterable accounting ledger for your database. Every financial transaction, every inventory adjustment, every customer profile update, before it's reflected in the main accounts, it is first meticulously documented in this ledger. This isn't just a record of committed transactions. It's a precise, sequential account of every single operation that modifies data within the database. It's like a ship's captain meticulously noting every course correction, every cargo loading, every significant event in the ship's logbook before the action is physically completed. Why is this write-ahead rule so crucial? It stems from the very problems we identified in the previous chapter: the speed difference between RAM and disk, and the risk of losing in-memory changes during a crash. By first forcing a record of the change to be written to a persistent, dedicated log file, the database gains a vital guarantee: the commit guarantee. A transaction is considered truly committed, and its changes durable only when its corresponding record or records in the write-ahead log have been successfully written to the persistent WAL file on disk. Only then does the database signal back to your application that the transaction is complete and safe. Let's walk through a simplified flow of a transaction with the WAL in play. Change in memory. You issue an update command to change a customer's phone number. The database loads the relevant customer data page into its RAM buffer pool and modifies the phone number. This page is now dirty in memory. WAL record creation. Immediately, before any further action is taken on the main data page, the database generates a concise but complete record describing this change. This WAL record doesn't contain the entire data page. It's much smaller and just outlines the operation. Transaction X. Update customer 123's phone number from YYYYYYY to ZZZZZZZ. It also contains some critical metadata, like a unique identifier for this log entry, often called a log sequence number, or LSN. WAL buffer. This tiny WAL record is first written to a small, dedicated in-memory buffer for WAL records. Transaction commit and flush. When your application requests to commit the transaction, the database takes the WAL records for that transaction and possibly other pending transactions in the WAL buffer, and flushes them to the dedicated write-ahead log file on persistent disk. This flushing process uses special system calls, like fsync, that bypass the operating system's normal buffering and force the data directly onto the physical storage device. This is the crucial step. Acknowledge commit. Once the fsync operation confirms that the WAL records are safely on disk, and only then does the database send the transaction committed successfully message back to your application. Asynchronous data write. The dirty data page in the main buffer pool, which now contains the updated phone number, can be written to the customer data file on disk later. This write happens asynchronously, in the background, often batched with other dirty pages. This deferred write is much more efficient because random writes to data files are slow. Why does this work so effectively? Sequential writes are fast. Writing to the write-ahead log is almost always an append-only operation. New WAL records are simply added to the very end of the log file. Writing sequentially is one of the fastest operations a disk can perform, especially for modern SSDs. This allows the database to achieve durability quickly. Small records, WAL records, are typically very compact. They describe the change rather than containing the entire changed data page. Writing a small amount of data sequentially is much faster than writing an entire, potentially large, data page randomly. Crash recovery cornerstone. If a crash occurs after the WAL records for a committed transaction are safely on disk, but before the dirty data pages have been written to their main storage location, the database can still recover. On restart, it simply reads the WAL file from a specific point, applies all the changes it finds for committed transactions, which were guaranteed to be durable by the WAL, and restores the database to a consistent state. It uses the WAL as its definitive instruction manual for recovery. The write-ahead log effectively decouples the immediate need for data durability from the slower process of modifying the large, random access data files. It's the ultimate insurance policy for your data. A small, yet mighty, guardian ensuring that your digital promises are kept, even in the face of unforeseen digital calamities. In the next chapter, we'll peel back another layer and delve into the intricate dance between WAL, checkpoints, and recovery, revealing how these components work together to provide truly robust data management. Chapter 5. How WAL works, a step-by-step journey. We've established the fundamental principle of the write-ahead log, recording every change before committing it, ensuring durability. Now, let's peel back another layer and explore the detailed mechanics of how this remarkable system truly functions, from the moment a change is envisioned to the system's ability to recover from a catastrophic crash. Logging. What goes into a WAL record? When an operation occurs, the database generates a WAL record. This isn't just a simple note. It's a precisely structured piece of information containing everything needed to recreate or undo the change. While the exact contents vary by database, common elements include log sequence number, LSN, a large, ever-increasing number that uniquely identifies each point in the WAL. It's like a digital odometer for the database's history. Higher LSNs mean more recent changes. Transaction ID identifies which specific transaction generated this log record. Operation type specifies what happened, e.g., insert, update, delete, create table, index build. Affected data, identifiers for the specific table, index, or data page that was changed. Change details, this is the core. For an update, it might include the old value for rollback, a sort of reverse instruction, and the new value for redo. For an insert, it's the new data. Sometimes, it contains an image of the entire data page before and after the modification to protect against torn page scenarios. These records are compact, packed efficiently to minimize the amount of data written to the log. They are then written sequentially to an in-memory buffer, awaiting their journey to persistent storage. Flushing, the critical act of durability. This is arguably the most crucial step for guaranteeing durability. When a transaction commits, its WAL records, along with records from other concurrent transactions that are also committing, are gathered in the in-memory WAL buffer. The database then issues a special command, typically an fsync system call on Unix-like systems or similar mechanisms on Windows to the operating system. The fsync call is a forceful one. It instructs the operating system to take all buffered data for that specific file and immediately write it out from the operating system's cache onto the physical disk. This bypasses any caching the operating system might be doing and ensures the data is truly durable, etched onto the magnetic platters or flash cells. If this fsync operation fails or is interrupted before completion, the transaction is considered to have failed and it will be rolled back. Without fsync, there's no guarantee that the data is truly on disk, leaving it vulnerable to power loss even if the database software thinks it wrote successfully. This fsync operation is the heart of the write-ahead principle. It's the moment where the database sacrifices a bit of speed, as disk I/O is slow, for an absolute guarantee of persistence. Checkpoints, managing the ever-growing log. If WAL records were only ever appended, the log file would grow indefinitely, eventually consuming all available disk space. Furthermore, a crash recovery scenario would mean replaying an enormous, potentially years-long log file, taking an unacceptably long time. This is where checkpoints come into play. A checkpoint is like taking a snapshot in time of the database's permanent data files. At a checkpoint, the database ensures that all dirty data pages in the buffer pool, whose changes have been written to the WAL and are considered committed, are safely written from memory to their respective data files on disk. Once a checkpoint is successfully completed, the database knows that all changes up to a certain log sequence number, the checkpoint LSN, are safely present in the main data files. This gives the database a safe recovery point. Any WAL records before this checkpoint LSN are no longer strictly necessary for crash recovery, though they are still valuable for other purposes, which we'll cover later. This allows the database to truncate the WAL. Older, unneeded WAL segments can be removed or reused, preventing infinite growth. Speed up recovery. After a crash, the database only needs to start replaying the WAL from the last completed checkpoint LSN, significantly reducing the amount of log to process. Checkpoints are typically performed periodically, either based on a time interval, e.g., every 5 minutes, or when a certain amount of WAL data has been generated. While essential, checkpoints can be I/O intensive, as they trigger a large number of disk writes for dirty data pages. Databases try to manage this efficiently, often by writing dirty pages gradually in the background. Recovery, rising from the ashes of a crash. Now for the ultimate test. What happens when the system crashes? Thanks to the WAL and checkpoints, the database can be restored to a consistent, trustworthy state. This recovery process typically involves 2 phases: preparation, finding the starting point. When the database restarts after a crash, it doesn't just open its data files. It first looks for the location of the last successful checkpoint within its internal metadata. This LSN tells the database where the safe, on-disk state truly lies. Redo phase. The database then reads the WAL files starting from that checkpoint LSN. For every change recorded in the WAL that was marked as committed, meaning its associated transaction successfully completed its fsync to the WAL before the crash, the database reapplies those changes to the main data files. This handles all the modifications that were durable in the WAL, but hadn't yet been written from the buffer pool to the actual database files on disk before the crash. This is how the durability in ACID is fully realized. Undo phase. It's possible that some transactions were in progress or actively running when the crash occurred, and thus their changes were never fully committed. their WAL records might be present, but without a commit marker. For these uncommitted transactions, the database uses information within the WAL or auxiliary undo logs, depending on the database's internal design, to undo any partial modifications they might have made to data pages. This ensures that only fully committed transactions survive, upholding the atomicity in ACID. Through this meticulous redo and undo process, the database is brought back to the exact state it was in right before the crash, but with all committed transactions preserved and all incomplete ones gracefully rolled back. The torn page problem is also mitigated, as the recovery process can overwrite any partially written pages with correct, consistent data from the WAL. The elegant interplay between logging, flushing, checkpointing, and the redo-undo recovery algorithm makes the write-ahead log a truly robust system. It sacrifices a small, sequential write up front to prevent massive data loss and guarantee consistency, making it the bedrock of data reliability. In the next chapter, we'll see exactly how these mechanics directly enable the critical ACID properties that define transactional databases. Chapter 6. ACID and WAL, the guardians of data integrity. In our journey to understand the write-ahead log, we've repeatedly touched upon the concept of database transactions. Now, it's time to solidify that connection by delving into the renowned ACID properties. ACID is an acronym representing 4 key characteristics that guarantee the reliability of database transactions: atomicity, consistency, isolation, and durability. The write-ahead log plays a direct and indispensable role in enabling at least 2 of these, and it indirectly supports the others. Let's quickly recap each of the ACID properties. Atomicity, A. As we learned, atomicity means that a transaction is treated as a single, indivisible unit of work. It either completely succeeds, all its operations are committed, or completely fails, all its operations are rolled back, leaving no partial results. There is no in-between state. Consistency, C. A transaction brings the database from one valid state to another valid state. This means that after a transaction completes, all predefined rules, constraints, triggers, and cascades, e.g., uniqueness of a user ID, positive balance in an account, referential integrity between tables, are maintained. It's about ensuring the data adheres to its established schema and rules. Isolation, I. This property ensures that concurrent transactions, multiple transactions happening at the same time, do not interfere with each other. From the perspective of each transaction, it appears as if it is the only transaction running on the system. The intermediate states of one transaction are not visible to other transactions until it is committed. Durability, D. Once a transaction has been committed, its effects are permanent and will survive any subsequent system failures, such as power outages, unexpected shutdowns, or database crashes. The changes are written to non-volatile storage and are guaranteed to persist. Now, let's explore how the write-ahead log acts as the primary enabler of these critical properties, particularly atomicity and durability. How WAL ensures durability. This is arguably the most direct and crucial link. Without the write-ahead log, guaranteeing durability would be incredibly difficult, if not impossible, in a high-performance database. As we discussed in Chapter 4 and 5, the WAL guarantees durability through a simple but strict rule. A transaction is considered committed, and its changes durable only when its corresponding WAL records have been safely written, flushed, to persistent disk storage. Consider this scenario. A bank transfer of $100 is committed. The database returns success to the application. At that precise moment, if the power instantly fails, what happens? Without WAL. If the database only modified dirty pages in RAM and hadn't yet written them to disk, the committed $100 transfer would be completely lost upon restart. The balance would revert to what it was before the transaction. Durability would be utterly compromised. With WAL, because the WAL records for that $100 transfer were forcibly flushed to disk before the success message was sent, those records are safe. When the database restarts, it will detect the crash, read its WAL from the last checkpoint, find the committed transactions records, and redo the changes to the user accounts. even though the original dirty pages were lost from RAM, the WAL provides the definitive instruction manual to reconstruct the committed state. Therefore, the WAL's fast, sequential, and guaranteed-to-disk writes are the bedrock of durability. It's the reason you can trust that your online purchase, once confirmed, won't magically disappear from the vendor's system. How WAL enables atomicity. WAL also plays a vital role in ensuring atomicity, the all-or-nothing principle. This comes into play during the crash recovery process we outlined in Chapter 5, specifically through the undo and redo phases. Redo for committed transactions. For any transaction whose WAL records indicate it was committed, but whose data changes had not yet been written to the main data files from the in-memory buffer pool, the WAL provides the exact instructions to redo those changes. This ensures that even though the system crashed, the committed transactions effects are fully applied, maintaining the all part of all or nothing. Undo for uncommitted transactions. What about transactions that were in progress when the crash occurred and never formally committed? Perhaps the user closed the application, or the database itself crashed midway through a multi-step operation. The WAL contains records for these partial, uncommitted changes as well. During recovery, the database identifies these incomplete transactions and uses the WAL, and sometimes a separate undo log, which is conceptually similar and often derived from WAL entries, to undo any changes they might have already made. This reverts the database to the state it was in before the transaction began, ensuring the nothing part of all or nothing. By providing both the ability to redo committed changes and undo uncommitted ones, the WAL ensures that the database always lands in a state where all transactions are either fully applied or fully discarded, thereby upholding atomicity. WAL's indirect role in consistency and isolation. While WAL doesn't directly implement consistency or isolation, it provides the solid foundation upon which these properties can be built. Consistency, indirect role. Consistency relies heavily on atomicity and durability. If transactions weren't atomic, or if their committed changes could vanish, then maintaining the logical rules and constraints of the database, e.g., account balance cannot be negative, would be impossible. By guaranteeing atomicity and durability, the WAL ensures that the database can recover to a valid state that respects its defined rules. Without WAL, any crash recovery would be a gamble, likely resulting in an inconsistent database. Isolation, indirect role. Isolation typically involves concurrency control mechanisms like locking or multi-version concurrency control, MVCC. MVCC is particularly relevant here. In MVCC, when a transaction modifies data, it often creates a new version of that data rather than overwriting it in place. Older versions are retained for other concurrent transactions that might be reading the data. The system uses transaction IDs and log sequence, numbers, LSNs from the WAL to determine which version of the data each concurrent transaction should see. The WAL, being the definitive sequential record of all changes, provides the essential ordered sequence of events and transaction metadata that makes complex MVCC systems possible and efficient. In essence, the write-ahead log acts as the primary guardian of data integrity, tirelessly ensuring that once you make a commitment to your database, it is honored, come what may. It transforms a volatile, crash-prone system into a reliable, trustworthy data store. In the next chapter, we'll see how these theoretical concepts manifest in the real world, examining how popular database systems like PostgreSQL, MySQL, and SQLite put WAL into action. Chapter 7, WAL in Action. Real-world database implementations. We've covered the theoretical underpinnings of the write-ahead log, its purpose, mechanics, and role in upholding ACID properties. Now, let's turn our attention to how these powerful concepts are put into practice by the relational databases we interact with daily. While the core principles remain consistent, each database system has its own terminology, file structures, and operational nuances when it comes to implementing WAL. By looking at a few prominent examples, we can appreciate both the universal need for WAL and the diverse ways it's engineered. PostgreSQL. PGWAL and XLOG. PostgreSQL, a powerful open-source relational database, uses WAL extensively and transparently. WAL directory and files. In PostgreSQL, the write-ahead log is stored in a directory typically named PGWAL or PGXlog in older versions, within the database cluster's data directory. Inside, you'll find a sequence of sequentially numbered files, often 16 MB each by default, like 10 quadrillion 1. These are the WAL segments, and new records are always appended to the current active segment. XLOG records. Internally, PostgreSQL refers to these records as XLOG records. These are low-level descriptions of changes, which page was modified, what bytes were changed, and so on. Checkpoints. PostgreSQL performs checkpoints periodically. These are triggered by either a time interval, e.g., checkpoint timeout parameter, default 5 minutes, or when a certain volume of WAL data has been generated, max wall size parameter, default 1 GB. During a checkpoint, all dirty data pages are flushed from PostgreSQL's in-memory buffer cache to the main data files on disk. The location of this completed checkpoint is then recorded, allowing older WAL segments to be archived or eventually recycled. Durability control, synchronous commit. PostgreSQL offers a parameter called synchronous commit that directly impacts how quickly transactions are truly durable. On default, this is the most durable setting. The database waits for the WAL records for each transaction to be fsync, D to disk before reporting, commit successful to the client. This offers the highest guarantee against data loss. Off. The database does not wait for the WAL records to be fsync, D. Instead, it writes them to the operating system's buffer, and the OS flushes them periodically. This can offer higher transaction throughput, but in the event of an immediate operating system crash or power loss, transactions that were committed very recently might be lost. This is rarely recommended for critical data. PostgreSQL offers other intermediate settings, local, remote-apply, for more granular control, especially in replication scenarios, balancing performance with varying levels of durability. MySQL InnoDB storage engine, redo log and undo log. MySQL, particularly with its most popular storage engine, InnoDB, also relies heavily on logging. InnoDB actually uses two primary logs for ACID compliance, the redo log and the undo log. Redo log, this is InnoDB's equivalent of a write-ahead log. It's primarily for crash recovery and durability. These sequential log files are typically named ibligfile0, ibligfile1, etc., and they operate in a cyclic manner. When the current log file fills up, InnoDB wraps around to the beginning of the first one, but only after ensuring that the data described by the overwritten part of the log has been safely written to the main data files. This process is part of InnoDB's continuous, fuzzy checkpointing. Undo log. While the redo log focuses on making changes durable and enabling crash recovery, the undo log is essential for atomicity, rolling back transactions, and isolation, supporting multi-version concurrency control, or MVCC. When data is modified, InnoDB writes the previous state of the data to the undo log. If a transaction needs to be rolled back, or if another transaction needs to see an older version of the data, as in MVCC, the undo log provides the necessary information to reconstruct that previous state. Critical parameter in nodflushlogiticscommit. This is one of MySQL's most impactful configuration parameters, directly dictating the performance durability trade-off for the redo log. 1. Default. The redo log buffer is flushed to disk fsync for every transaction commit. This provides full ACID durability. In case of a crash or power failure, no committed transactions are lost. This is the safest but potentially slowest option. 0. The redo log buffer is written to the OS cache at commit, but fsync to disk happens only about once per second. This offers maximum performance and is suitable for non-critical data or where the application can tolerate losing up to 1 second of committed transactions. A power outage could mean losing recent data. 2. The redo log buffer is written to the OS cache at commit and the operating system is instructed to flush its buffer to disk about once per second. This is similar to 0 in terms of data loss risk from power failure, but offers higher protection against a MySQL server crash, as the data would at least be in the OS cache. Case study. In Nodflashlogic in action. Imagine a high-frequency trading platform. Losing even a single trade is unacceptable. Here, in Nodflashlogic equals 1 would be mandatory, even if it meant slightly lower transaction rates. The durability guarantee is paramount. Now consider a web analytics logging system, capturing millions of user clicks per hour. Losing a few seconds of click data in a rare server crash might be an acceptable trade-off for the significantly higher throughput gained by setting in Nodflashlogic equals 0. The vast volume of data makes frequent fsync calls a performance bottleneck, and the data itself might not be strictly critical. This parameter illustrates the continuous balancing act between performance and data safety that database administrators must consider. SQLite WAL mode. SQLite, the immensely popular embedded database, has a more unique approach. Its original default journal mode, journal file, isn't a true WAL. Instead, before modifying a database page, SQLite would write the original content of that page to a separate rollback journal. If a crash occurred, the journal was used to restore the original pages. This was simple but imposed significant concurrency limitations, writers block readers, and vice versa. To address these limitations, SQLite introduced WAL mode. Database WAL file. In WAL mode, all database changes are appended to a separate WAL file, e.g., MyDataDB WAL. Database SHM file. A shared memory file, MyDataDB SHM, is used for coordination between readers and writers, indicating which parts of the WAL are valid and need to be seen. Concurrency. This is the game changer for SQLite. Readers can access data directly from the main DB file and consult the WAL file to see more recent committed changes. This means multiple readers can operate concurrently without blocking a single writer. The writer simply appends changes to the WAL file. Checkpointing. Changes from the WAL file are periodically checkpointed, moved back into the main DB file. This can happen automatically in the background or be explicitly triggered. This manages the size of the WAL file and ensures the main database file is eventually updated. SQLite's WAL mode demonstrates how the core WAL concept can be adapted to vastly different database architectures, from large client-server systems to tiny embedded ones, to enhance essential features like concurrency while maintaining durability. Common threads. Despite their differences, these database implementations share fundamental principles. Sequential writes all leverage the speed of appending changes to a sequential log file. Forced syncs all employ mechanisms, fsync, to push changes directly to durable storage for committed transactions. Recovery all use their respective logs to perform redo and undo operations after a crash, bringing the database to a consistent state. Understanding these real-world applications solidifies the abstract concepts of WAL and showcases its universality as a foundational technology in data management. In the next chapter, we'll move beyond crash recovery and explore the many other powerful applications of the write-ahead log. Chapter 8, Beyond Recovery, WAL for Replication and Streaming. Thus far, we've focused almost exclusively on the write-ahead log's primary mission, guaranteeing data durability and enabling robust crash recovery. This alone makes WAL an indispensable component of any reliable database. However, the elegance of the WAL, its precise, sequential, and immutable record of every database change, lends itself to a host of other powerful applications that extend far beyond simply recovering from system failures. In this chapter, we explore how WAL serves as the backbone for high availability, disaster recovery, and real-time data streaming. Replication, ensuring high availability and scalability. Imagine a critical online service. If its single database server fails, the entire service goes down. This is where replication comes in. Replication is the process of creating and maintaining identical copies of a database on separate servers. If the primary database fails, one of its copies, known as a replica or standby, can quickly take over, minimizing downtime and ensuring continuous service. Replicas can also be used to distribute read traffic, improving scalability. How does WAL facilitate this? It's remarkably efficient. Instead of having to copy entire data files or complex snapshots between servers, the database simply streams its write-ahead log records to the replicas. Physical replication. In this common method, used by PostgreSQL streaming replication, for instance, the raw WAL records are continuously shipped from the primary database to one or more standby servers. Each standby server receives these records and applies them to its own copy of the database files. This keeps the standby a byte-for-byte exact duplicate of the primary, often with only a few milliseconds of lag. If the primary fails, a standby can be promoted to become the new primary with very little data loss, depending on whether replication is synchronous or asynchronous. This is highly efficient because only the small, sequential changes are transmitted, not large data blocks or network-intensive diffs. Logical replication. Some databases, like PostgreSQL's logical decoding or MySQL's binary log, which serves a similar function to WAL for replication, can decode the WAL into a more abstract, logical representation of changes, e.g., inserted row X into table Y, or updated column Z of row A from value B to value C. This logical stream of events can be used for heterogeneous replication, replicating data between different versions of the same database or even to a completely different type of database system. Selective replication, replicating only specific tables or schemas to a standby. Data transformation, applying transformations to the data before it's applied on the replica. In both forms, WAL's ordered record of events makes it the perfect transport mechanism for keeping multiple database instances synchronized, underpinning high-availability architectures that are essential for modern applications. Point-in-time recovery, PITR, rewinding database history. Beyond simple crash recovery, the write-ahead log enables an incredibly powerful feature. Point-in-time recovery, PITR. Imagine an administrator accidentally deletes critical customer data from the production database. A simple crash recovery would restore the database to its state just before the crash, but in this case, the deletion was a committed transaction, so a standard recovery wouldn't help. This is where PITR shines. PITR allows you to restore a database to any arbitrary moment in time, e.g., 2:37 p.m. last Tuesday, just before the accidental deletion. This magic is performed using two core components: a full database backup, a snapshot of your entire database taken at a specific point in time, e.g., Sunday night's backup, an archive of WAL segments. All the WAL segments generated since that full backup are continuously shipped to a long-term, durable storage location, often referred to as the WAL archive or WAL shipping. To perform PITR, you would restore the full database backup to a new or recovery server. This brings you back to the state of Sunday night. Then, starting from the LSN of that backup, you apply, or replay, the archived WAL segments sequentially, just like in crash recovery. You continue applying these changes until you reach the exact LSN corresponding to your desired recovery point, e.g., 2:37 p.m. Tuesday. Because the WAL is a complete and ordered log of every modification, you can stop the recovery process at any point along this timeline, effectively rewinding your database to a precise historical state. This is invaluable for recovering from user errors, application bugs, or even malicious attacks. Change data capture, CDC, and data streaming. One of the most exciting and increasingly vital applications of the write-ahead log is in change data capture, CDC. CDC is the process of identifying and capturing changes made to a database, and then delivering those changes in real time or near real time to other systems. The WAL is the ideal source for CDC because it is, by its very nature, a detailed, ordered, and complete history of every change. Databases can expose interfaces, e.g., logical decoding in PostgreSQL, or reading the binary log in MySQL and decoding it, that allow external applications to tap into this live stream of changes. What can this live stream enable? Real-time analytics and data warehousing. Businesses can feed changes directly into their data warehouses or big data platforms, allowing for up-to-the-minute dashboards, business intelligence, and real-time decision-making, rather than relying on batch updates. Microservices communication. In a complex microservices architecture, CDC allows different services to react to changes in data without direct coupling. For example, an order service might generate changes that are captured and streamed, allowing a separate inventory service to update stock levels, or a notification service to send out an order confirmation email, all triggered by the database change itself. Search indexing, keeping external search indexes, like Elasticsearch, synchronized with the primary database. Data synchronization, maintaining highly consistent copies of data across various systems, caches, or applications. Think of the WAL as the database's internal, real-time broadcast channel of events. Beyond just being used internally for recovery, this channel can be securely tapped into for a multitude of purposes, allowing data to flow and react across an enterprise, powering everything from immediate customer notifications to critical business analytics. The versatility of the write-ahead log truly transforms it from a mere recovery mechanism into a foundational component for building robust, scalable, and highly available data-driven systems. Its simple yet powerful design stands as a testament to efficient engineering. In the next chapter, we'll delve into the practical operational considerations and tuning aspects necessary to leverage the WAL effectively, balancing performance with the critical need for data integrity. Chapter 9. The performance and operational aspects of WAL. By now, it's clear that the write-ahead log is essential for data integrity, recovery, and advanced features like replication. However, like any crucial component, understanding its operational characteristics and performance implications is vital for database administrators and system architects. The WAL brings immense benefits, but it also imposes overhead and requires careful tuning and monitoring to ensure efficient database operation. The overhead of WAL. While incredibly efficient for what it does, WAL isn't free. There are inherent costs associated with its operation. Write latency. Every committed transaction, regardless of how small the actual data change, requires its corresponding WAL records to be written and F-synced to disk. This synchronous disk I/O is often the slowest part of a transaction's commit time. In environments with very high transaction rates, thousands of transactions per second, this can become a significant bottleneck if the underlying storage for the WAL is not extremely fast. Disk space consumption. WAL files and their archives for PITR and replication consume disk space. For busy databases, this can amount to gigabytes or even terabytes of data daily or weekly. Unmanaged WAL growth can fill up a disk and bring the database to a grinding halt. CPU usage. Generating WAL records and managing the WAL buffer, flushing, and checkpointing processes require CPU cycles. While typically not the primary bottleneck, it adds to the overall server load. Tuning parameters, balancing performance and durability. Database systems provide various configuration parameters that allow administrators to fine-tune WAL behavior, often involving a trade-off between performance, durability guarantees, and recovery time. WAL buffer size, e.g., WAL buffers in PostgreSQL, in NodBlig buffer size in MySQL. This parameter controls the size of the in-memory buffer, where WAL records are temporarily stored before being written to the WAL file on disk. Larger buffers can accumulate more transactional changes before needing a disk flush. This can reduce the number of F-sync calls, particularly for workloads with many small, concurrent transactions, potentially improving throughput. Smaller buffers, more frequent flushes, potentially leading to higher latency for individual transactions if not enough data accumulates between flushes. Trade-off. Larger buffers consume more RAM. An optimal size balances disk I/O reduction with memory usage. Commit behavior /F-sync, frequency. e.g., synchronous commit in PostgreSQL, in nodflushlogetics commit in MySQL. As discussed in Chapter 7, these parameters directly control when the database performs the fsync operation for WAL records. Maximum durability, e.g., PostgreSQL on MySQL 1. Every transaction commit waits for its WAL records to be safely on disk. Highest data safety, but potentially slower due to frequent I/O waits. Relaxed durability, e.g., PostgreSQL off MySQL 0 or 2. WAL records may be written to disk less frequently, e.g., every second or only when the buffer is full. This can significantly increase transaction throughput as individual commits don't wait for disk I/O trade-off. Performance gains come at the risk of losing recent committed transactions if a crash occurs immediately after the application receives a commit successful message, but before the physical disk write occurs. The choice depends entirely on the application's tolerance for data loss. Checkpoint configuration, e.g., checkpoint timeout, max WAL size in PostgreSQL. These parameters control how frequently checkpoints occur. Frequent checkpoints lead to smaller amounts of WAL to replay during crash recovery, which means faster recovery times. However, they also cause more frequent I/O spikes, where the database has to write a large number of dirty data pages to disk, potentially impacting runtime performance. Infrequent checkpoints result in larger WAL files, more records to process during recovery, and longer recovery times. But they reduce the frequency of I/O spikes, leading to smoother runtime performance with fewer background write operations impacting foreground tasks. Trade-off: balancing recovery time objectives, RTO, with continuous operational performance. Storage considerations. The storage used for the WAL is paramount to database performance. Dedicated, fast storage. For high-performance database servers, it is a common best practice to place the WAL files on a dedicated, high-speed storage device, e.g., a separate NVMe SSD. This isolates the highly sequential write pattern of the WAL from the more random read-write patterns of the main data files, preventing I/O contention. Reliability. The WAL storage must be fault-tolerant, e.g., RAID 1 or higher, to protect against disk failure. If the WAL itself is lost, recovery can become impossible, leading to catastrophic data loss. Archiving strategy. For PITR and replication, a robust strategy for archiving completed WAL segments to a safe, external, and highly available location, e.g., cloud storage, network-attached storage, is critical. This process must be efficient to avoid accumulating stale WAL files that consume valuable local disk space. Monitoring WAL activity. Proactive monitoring of WAL-related metrics is essential for maintaining a healthy database. WAL generation rate. Track how many WAL bytes per second or minute the database is producing. A sudden spike might indicate an unusual workload or application bug, e.g., an update statement affecting many rows inefficiently. A slowdown might indicate a bottleneck. WAL disk usage. Regularly check the disk space consumed by the WAL directory. If it's growing unusually large, it could indicate archiving failures, checkpointing issues, or simply an unexpectedly high transaction volume. Running out of WAL disk space will halt the database. Checkpoint frequency and duration. Monitor how often checkpoints are happening and how long they take. If checkpoints are too frequent or taking too long, it can signal an I/O bottleneck on the data disks or an oversized write workload. Fsync, latency. Specialized tools or operating system monitors can track the latency of fsync, calls to the WAL device. High latency here directly translates to higher transaction commit times. Common pitfalls. Putting WAL on slow storage. The fastest disk in your server should be dedicated to the WAL. Placing it on the same slow disk as everything else will throttle all write operations. Ignoring archiving failures. If WAL segments aren't being archived for PITR replication, they will accumulate and eventually fill the disk, causing an outage. Misconfiguring durability. Setting in nodflushlogetics commit or synchronous commit to a relaxed setting without understanding the data loss implications for the business. inadequate checkpoint tuning, leading to either very long recovery times or excessive I/O during runtime, both of which are undesirable. Effectively managing the write-ahead log is a crucial part of optimizing database performance and ensuring its long-term stability and recoverability. It requires a deep understanding of the database's workload, careful configuration of its parameters, and diligent monitoring of its behavior. In the final chapter, we'll look to the horizon, considering how the fundamental principles of WAL continue to evolve and adapt to new technologies and the ever-growing demands of the digital world. Chapter 10, The Future of WAL and Data Persistence. Throughout this book, we've journeyed from the fundamental concept of data persistence to the intricate mechanics of the write-ahead log. We've seen how this unsung hero tirelessly works behind the scenes, ensuring the atomicity and durability of our transactions, enabling quick recovery from crashes, and serving as the lifeblood for replication, point-in-time recovery, and real-time data streaming. Its simplicity in concept belies its profound impact on the trustworthiness and resilience of modern database systems. The WAL principle, writing a sequential log of changes before applying them to the main data store, is a foundational pattern that predates modern computers and databases, hearkening back to the meticulous ledgers of ancient accountants. Its enduring power lies in its elegant solution to the inherent conflict between the speed of volatile memory and the permanence of slow, non-volatile storage. WAL in an evolving landscape. While the core principles of WAL are timeless, the technological landscape around databases is constantly shifting. Here's a glimpse into how WAL, or its conceptual descendants, is adapting and evolving in response to new challenges and innovations. Cloud and distributed environments. In elastic cloud environments, databases often run in highly distributed ephemeral containers, where local storage might be temporary. Here, WAL segments are increasingly shipped to highly durable, disaggregated cloud object storage, like Amazon S3 or Google Cloud Storage, as they are generated. This turns WAL into the primary replication channel across distributed nodes, ensuring consistency even when individual nodes fail or scale up down. The log becomes a global, shared, immutable record across an entire cluster. Persistent memory, PMEM NVM. This is perhaps the most disruptive innovation on the horizon for traditional WAL. Persistent memory, such as Intel Optane DC persistent memory, offers capacities closer to DRAM, but retains its data even after power loss. If WAL records can be written to PMEM, the costly F-sync. Operations common with traditional disk storage could become orders of magnitude faster, potentially achieving truly instant durability without the high latency penalty. This could fundamentally change how databases manage their buffer pools and flush strategies, accelerating commit rates dramatically. Log-structured merge trees, LSM trees. While not WAL in the classic relational database sense, LSM trees, popular in many NoSQL databases, like Apache Cassandra, RocksDB, and Google Bigtable, embody the log-first philosophy on a grand scale. All writes initially go to an in-memory buffer, then are flushed as immutable, sorted files to disk. Reads often have to consult multiple layers of these files. The durability and consistency in LSM trees are built around the idea of immutable, append-only logs of sorted data, showcasing the enduring power and adaptability of the logging principle for massive-scale, write-heavy systems. Disaggregated storage and computational storage. As compute and storage resources decouple, efficient remote storage and specialized computational storage units that can perform operations closer to the data will pose new challenges and opportunities for WAL. The sequential, localized nature of WAL writes will need to be optimized for high-speed network transfers and potentially for in-storage processing. The enduring power of the log. Regardless of the new hardware, architectural shifts, or database paradigms, the fundamental concept of an ordered, append-only journal of changes remains incredibly powerful and central to data persistence. Why truth source? A sequential, immutable log is the ultimate source of truth. It precisely records what happened when it happened and in what order. There's no ambiguity. Concurrency control. The log's inherent ordering simplifies how concurrent operations are managed and resolved. Efficiency. Sequential writes are inherently faster than random writes, a physical property that persists across storage technologies. Auditability and reproducibility. A complete log allows not just recovery, but also detailed auditing and the ability to reproduce historical states. In conclusion, the write-ahead log, though often unseen and unappreciated by the end user, is a marvel of computer science engineering. It's the invisible guardian of our digital trust, the silent enabler of our always-on world. From ensuring your individual bank transfer is secure to powering the vast, distributed systems that define our global economy, the principle of sequential logging for durability and consistency will continue to be a cornerstone of data management. As technology evolves, the WAL, or its conceptually refined descendants, will no doubt continue to adapt, securing our data in an ever more complex and data-driven future. The unsung hero, indeed.